Good stuff. All right. Thanks, everybody, for joining today. It's my pleasure to introduce Rupen Patel. Rupen was the former CTO and CEO of Influence Health, and I worked with him for several years. One of the areas that Rupen's been focused a lot on is big data infrastructures. Influence Health was, in fact, an aggregator of large sets of clinical and behavioral data on individual patients and consumers, built and had to build a really strong and robust data infrastructure to bring in data feeds, blend those data feeds, and then create value and views and insights from all that data. And today we've asked Rupen to talk about the big data infrastructure and specifically the emerging patterns to build a big data infrastructure going forward, with a real emphasis on sort of having a scalable, and I don't just mean technically scalable, but a scalable solution to the idea that there are many use cases and many approaches to doing this over time, and one hates to have to replumb and refoundation every couple of years. So it's a little technical and detailed, but this is the nature of these things, and the point of these is to go deeper than the normal sort of Time magazine level hand waving around this stuff. So with that, let me turn it over to Rupen. Rupen, welcome and thanks.
Thank you, John, and thank you everyone for taking your lunch hour to attend this presentation, and look forward to talking about big data infrastructure and some of our learnings over the past few years. So in the time that we've done this introduction, over 200 million emails have been sent across the world. We all know this data is growing at an exponential rate. And in order to handle that exponential rate of growth, there's been a proliferation of tools in the market, thousands and thousands of tools and infrastructure components. In fact, if you follow the LinkedIn Emerging Jobs Report, 3 of the top 10 jobs for 2020 are in the data infrastructure, data engineering, data science space. There's now formal titles for a lot of what we used to do kind of informally, data engineers, ML, AI ops, data scientists, et cetera. So a lot going on, as we all know. And it's been happening for over a decade. And the first half of the decade was really about the big part of big data, so the scaling part. Today, that's mostly handled by the cloud. And the cloud, of course, rides on some very advanced hardware, hardware that you can actually buy yourself and run for your own house network, like our home network, like I did. But the problems that aren't really solved today are really around the patterns for common use cases. And so that's what we're going to talk about a little bit today. So there's patterns that kind of span a range of use cases, from industry-specific needs to just generalized needs. And I won't be able to cover every single specialized pattern, but I wanted to cover one today that is generally applicable to a lot of companies. And it really tries to solve for another concrete issue, which is the wrangling of the data. And if you follow, again, data science world, Anaconda did a survey recently of about 2,000 data scientists, and they all indicated that about half of their time goes into just wrangling data. You could actually say maybe a little bit more than half. And as a result, there's been a ton of venture capital investment in the data wrangling world. And you've seen a few of the recent big hits like Snowflake and Segment out there. But the problem's still not solved. And that's the reason there's still a lot of investment in this space in terms of technology. And so what really is the problem? The way I like to kind of think about the problem space first, before sort of going into any kind of recommendation or ideas around solutions, is really to kind of break it down along as much of orthogonal axes as possible. And as Fred Brooks, essentially pointed out in his No Silver Bullet article, there's different kinds of complexity, but they kind of bucket into essential or accidental for the most part. So the essential complexity in data infrastructure is really around the change around the data itself over time. The accidental complexity is around the infrastructure and all the different nuances of managing it. And then there's this other dimension, which is sort of outside of that, which is economic. And it's the cost and how to kind of manage around understanding what the long-term management of the platform is going to cost us. And so I'll talk a little bit about these areas just to give a flavor for what we're really trying to solve for when we think about data infrastructure patterns. So the data asset management problem is a long-term problem. And it really relates to after a system's deployed. New sources are going to come in, existing sources are going to change, how you represent them is going to change due to tech changes, your business rules, schemas are going to change, et cetera. And how you handle all this change will determine whether the velocity of your development processes continues or whether it still slows down, i.e. tech debt. It also determines how many errors you're going to encounter later on downstream. Good story here is I was at NCR heading up tech for the small business division, and we were looking at another company, which is an analytics player specialized in our space that had a few hundred accounts. We ended up buying them, but they had a lot of tech debt. And what we ended up inheriting was about 2,000 stored procedures and about 1,000 tables. So their idea of managing change was when new accounts came on, they would fork some of the tables, add some more stored procedures, et cetera. And you can imagine the amount of really late nights that were required in order to maintain that system and how slow it was to change it once we got a hold of it. The other bucket of change is really around, or complexities around the infrastructure. And I won't go to all these. There's just too many of them unless, I want to put you to sleep here. But the main one I think to point out is just the managing of integrity of the data across reloads. And this turns out to be a really hard thing to do, particularly at scale, and particularly when there's a lot of complex pipelines. And if you're managing code and you're in the software development side of things, in general, code, once it executes, it loses its state, and then it gets to start all over again. Data is quite the opposite by definition. The state stays forever. So if you make a mistake in the data, it just compounds over time. And so how do you evolve systems such that you know what happened to the data and you can manage the integrity of it over time? That's a pretty challenging sort of aspect of this. And if you're following the elections right now, I'm in Georgia, and in Gwinnett County, there were a bunch of ballots that were pushed through the system, and there were a bunch of batches that each had one error in them, which caused the machines to sort of throw up, and now they're having to go back and manually recount everything. So just a concrete example of how not so simple it is to ensure item potency. And then the third dimension, of course, is cost predictability. And, we used to have the good old days where you just bought everything by the server, and it was easy to kind of understand what the cost is going to be long term because I just buy X number more servers. Then it went to more the core count, how many cores are you buying? And then it was some kind of virtualized unit, which was a combination of a core and some IO. And then now we have pricing models that are about credits. So we're really far decoupled from the actual hardware that they're purchasing indirectly. And it's a little harder to understand what that's going to cost us long term. And so we have to spend more time these days understanding what our workloads are going to be, how many environments we're going to have. Do we have a development process that's a little bit, very disciplined or not disciplined in terms of turning things on and off? So how much contingency do we have to build into our budget? But these are just things to keep in mind as technology's evolved. So have pricing models, and you have to factor those in to the solution. So then with all these problems, what's a good stable pattern for managing them and still being productive and getting value created very quickly from all of this data? Because at the end of the day, having data is one thing and producing value is actually what our goal is. So the pattern I want to talk about here is something we call the data refinery. And it really boils down to a couple of things and managing those things in the right ways. The first is, when do you process data? The second is, where do you process data? And then the third is, how do you manage the life cycle of change related to all those transformations over time? And so when you kind of think about all these things holistically, a pattern starts to emerge. At least for us, it has. It's something we use at Influence Health, and I've seen it at other companies that I've been involved in as well. And so I'm not saying this pattern is the only pattern. Certainly there's multiple patterns, but this is, I think, a fairly common pattern that could be potentially useful to a lot of folks. So at a high level, I'll just kind of go through the components of this so that everybody has an understanding of what makes up this pattern. The first at the top is almost every application, whether it's a web application or a mobile application, needs to have some kind of analytics so you can understand what users are doing with it. Most of those solutions today, the good news is, are pretty much baked. You can just buy them off the shelf and use them. things like Heap or Mixpanel or Google Analytics, et cetera. But the data that comes out of those products is still useful for further transformation. So you could take the usage data and sort of correlate it with, are we selling more software to the people who are using it? Or you could take the errors coming out of the product and say, are we losing customers because of those errors? There's a bunch of different questions you can answer with the exhaust of that data, which is why it's important to pump it into the rest of the refinery. And so going down a layer to the core of the refinery, really the first subsystem of the refinery is the data sourcing subsystem. And I label this as a subsystem because in a lot of companies that have been in, it's been an afterthought. You just kind of, go pull some files on a file system or set up an FTP server box or set up an API that somebody's going to push to, but it's not considered a formal subsystem. The challenge with that is over time, change happens. Those incoming schemas keep changing. You have to replay things. You have to see if what they sent you was the right thing. So there's a bunch of different needs there. And so you kind of have to think of the data sourcing area as a component and a system component you're going to formally manage and design around. Once the data's in, the data needs to be at least minimally processed so that the rest of the system can make some assumptions about it. Are you making sure that there's no integer values in string fields, for instance? Are you standardizing it into a format that everybody else downstream, all the other components downstream are going to understand? So that basic cleansing and normalization is yet another subsystem because all of those different sources are going to need to be standardized in a certain way. And what we do as the best practice is keep different buckets where we store the raw data so we can always go back and look as to what we got and have some kind of record of that. And then we store all the cleansed and normalized in another bucket. And the structure under those buckets is a design exercise. Do you store it by time, by customer and time? What do you archive off? What are the security requirements around that and provenance requirements around that? So there's a lot to do there. And those are formal kind of subsystems in this pattern. The good news is today, there's a lot of new vendors out there that are combining these into a as a service offering. And you've probably heard of a lot of them. Stitch is a good one, Fivetran, and Segment, which was recently bought by Twilio for about $3 billion, has a good solution here, including a CDP. So once the data has been cleansed and normalized, it goes into the set of pipelines that will transform it into the aggregations that are needed for downstream usage. And so you could take in, say, individual transaction entries from a point of sale. You can summarize them by point of sale and cashier so that you can generate a report. All of that transformation happens in a subsystem. And that's the core of the refinery. And then finally, the output of those pipelines ends up in some kind of a reporting layer. And that could be Tableau, or it could be Power BI, it could be a variety of reporting solutions. Below all of this and supporting all of these different transformations is the data layer. And inside the data layer, there's a few key components, and I'll quickly kind of go through these. The first is a data lake. As I mentioned before, we usually have a raw and a clean at the very least in the data lake. The data lake is just storing all of the data and makes it available at scale. Then there's a data catalog, which scans across the data lake and pulls out the schema. So it infers the schema, or you explicitly tell the data catalog what the schema is for that incoming data. And this is a vital component because all of the new tools these days need a data catalog in order to be able to query the data lake at runtime. So this data catalog acts as an external shared schema for all of that raw data and cleansed data. The next component is the data lakehouse, which is a new term. You've probably heard floating around. Spark, or Databricks rather, sort of popularized this idea. But it's basically the ideas from Hadoop, which is to bring the compute closer to the data. Thereby, you save all the work of moving it in and out of the storage layer. And you can also be more efficient. You can optimize how you do the compute. Inside of the lakehouse, one of the things we've found vital is to make sure we have a good way of handling all of our intermediate materialized views and tables. And what these are kind of aggregations of data that are intermediate level and will be reused later in other kinds of computation. A good example is we get EMR records in that have encounters. So every visit a patient makes is an encounter record. But all of the reporting and all of the logic we want to do is at the patient level, it's a person level, not at the encounter record level. So we create a materialized view where we combine all encounters through time for a patient. We remove redundancy, we dedupe it, we clean it, but we have this kind of unified view of all records for a patient under a patient object. And so that view is a materialized view that lives long-term and keeps getting updated. And so all the downstream processing can rely on that view and not have to recompute that all the time. And then finally, there's the data mart. This is where the final results of the aggregations are stored so that the reporting layer can report against it. And this is your typical star schema, snowflake schema, living inside of an OLAP database. The new addition these days is really the data science lab. And this is where ad hoc investigation of all this data occurs. And so data scientists want to be able to access all the data and do different kinds of analysis to figure out what they might need to use in terms of features for their models, model training. So all of this happens in the data science lab, which has connectivity to the data layer. And the data scientists can use their Python notebooks, they can use their TensorFlow libraries to do training, and then they can serve those models up for applications to use downstream. So I went a little bit quickly through that, and I'm sure you'll get a copy of this so you can kind of look at that later. But I wanted to set this up because I think this is the framework for what we do at Influence Health and a lot of other companies, and hopefully this will be valuable to you as a pattern. So I mentioned earlier there were 3 elements to this pattern, the first being when to process, second being where to process, and the third being how you manage change. And so that's, I think, a key piece of this that I want to go through. The first is when you process. And out there, you're probably familiar with ETL versus ELT. ETL is doing transformations from the raw or cleansed data sort of in another system and then pumping it into a data warehouse. You're doing the transformations first, and then later on, you're going to report on them. Now, the challenge with this is it implies that you know all of the different reporting requirements you're going to have in the future. And it also limits the data that you have access to in the event that you were wrong, because by definition, you pre-processed and only took out what you needed to put into the data warehouse. The contrast to that, and what we do, is the ELT approach, which is to do the processing on all that data sort of at the last minute when you need it, the closest to when you need it in time. What this allows is to have all of the data available to you to be wrong, frankly, because a lot of times you are wrong. You don't necessarily know what you don't know. You don't know what all the future requirements are. But if you have access to all the data inside of, say, a data lakehouse, you can run all the computations on it at a later time. And then you can, of course, cache results for speed, or you can just keep using dynamic queries against the lakehouse as you need them. And so we found this a very effective pattern to manage all the change and the velocity that we need to achieve in order to get results out quickly. The second part of this pattern is where to process. And so I alluded to this earlier. In the traditional world, there's a data warehouse, which is a OLAP database. The results of the ETL process are computed and put there. And then, of course, other systems can query that, or slices can be taken out into other data marts. What we do is use the data lakehouse pattern. There's several technology components that implement this today, sort of halfway. So you kind of there's a little bit of work you have to do to fully realize it. But between Spark and Delta Lake and Snowflake or Redshift and Spectrum, there's a couple of different solutions that kind of implement this pattern. And so we use the lakehouse pattern. All the cleansed data flows into the lakehouse, so the whole corpus of information is available. The data catalog then allows the lakehouse to understand what the schema of all that data is. And then we create intermediate views from that data, as I mentioned before, with the example of turning encounter records into people objects that have all the encounters under them. And then this allows future queries to be quick. This also enables ad hoc analysis by our data scientists, because they can directly hit the data lakehouse and have access to all the information, of course, with appropriate security and partitioning of data. So the lakehouse becomes a key part of this pattern. And then the third, as I mentioned, how to manage the life cycle, the long-term viability of this platform. I wanted to talk about a couple of different sort of concrete ways in which, one, I've seen it done, and one, we've done it. So in shops that don't have a lot of data engineers or a lot of expertise with data engineering, what I've seen, at least recently, as a popular solution is to use SQL. So just use SQL, don't use any specialized code in the data transformation layer. And the SQL statements can be run against any one of a multitude of data lakehouses, right? You could run it against Redshift Spectrum, you could run it against Snowflake, and both of those technologies allow you to access all of the data on your S3 buckets. And the transformations then just being done in SQL now need some tool to manage the proliferation of all that SQL and how to kind of box it in so that you can manage it as code. And so a very popular tool out there is dbt. I was talking to one of the leads over at Auth0, and they said they'd standardize on dbt as their tool set to manage their SQL-based transformations. So this becomes a very powerful pattern, again, the data refinery pattern, and this becomes a powerful sort of implementation of it if you don't have a lot of developers that are familiar with Spark or want to learn it as a transformation layer. And then the second incarnation of this is just using something like Spark or PySpark. And the advantage here is that there's the opportunity to do micro batches and sort of simulate real-time streams. Not quite real-time, so it's not quite streaming, but for most applications, it'll sort of get you there. But more importantly, you can do very complicated transformations. You can do machine learning algorithms using Spark as well, because there's a lot of libraries that plug into it. And what you'll notice here, it's the same exact pattern. So in the background, you'll see the shaded boxes, but instead of using something like a dbt, now we're using Spark. And this is mostly what we settled on at Influence Health, using Spark across our enterprise, and then using SQL kind of selectively where we needed to use it. And the Spark transformations run across a cluster, which Amazon's providing a lot of sort of help to manage. There's EMR, and then there's what's called Glue 2.0, which allows you to do kind of smaller PySpark jobs so that you don't have to manage the infrastructure. So kind of moving on here to the Lakehouse component itself. So I mentioned that the core piece of this in terms of where to process was the Lakehouse. And I wanted to just spend a few minutes on the 3 different types of Lakehouses that at least we've used and our impressions of them from using them for a while. And of course, this is going to change over time and evolve because technology always keeps evolving. So I'll start with Snowflake because it is in the news a lot, and a lot of people are using it, including us. From a data asset management perspective, in terms of managing the workflow of change over time, I kind of think it's average because it's just all SQL, right? And SQL's good, but it's not quite as plugged into your normal workflows as code is. And so there's just average level support to managing change with respect to doing any kind of transformation using SQL. And so Snowflake gets an average there. With respect to cost of operations, Snowflake uses a credit-based pricing model, which, as I said, kind of decouples the pricing from the workload. And it does tend to get expensive when you use it for complicated transformations because it uses more credits. And so it's not quite the best solution if you have, for a lakehouse, if you have a lot of computation you need to do, a lot of transformations you need to do. With the caveat that if you have a huge budget, it probably doesn't matter. But for those companies that are sort of budget limited, doing expensive transformations in Snowflake really adds up in terms of credit usage. So moving on, and I won't go through all these, but the transformation support's just as good as any other SQL database. What's great about Snowflake and better than almost everything else is it's just level of operational support. There's almost no administration with Snowflake. It's a pleasure to use. And of course, as a BI and OLAP solution, it's spectacular. It supports some really advanced data types like variants that let you do queries against sort of semi-structured data as well as the regular structured data. It's a fantastic OLAP BI solution with almost no administration. So on the flip side, Spark is fantastic in terms of its transformation capability because that's what it's built for. From a cost perspective, it's a little cheaper long-term if you're doing a lot of computation. And from a change management perspective, it's pretty good because you're using code to do all your transformations. So you have Git and all the other tools around that. It's not the right solution for doing OLAP or BI queries. It's not a real-time database, and there's a lot more administration with it. So that's the trade-off there. And Redshift sort of sits in the middle, I would say. Cost-wise, it does a pretty decent job. From an operational standpoint, there's a little bit higher burden than Snowflake. And from some of the bells and whistles perspective, it's a little bit less robust than Snowflake. Still solid solution, and Amazon keeps improving it, and it's plugged into their infrastructure pretty well. So we've used all three of these, and what we end up is usually picking two. And so we end up using Spark for our lakehouse and for doing all the complicated actions. And then we use Snowflake at Healthgrades, and we used Redshift at Influence Health for doing all the OLAP and BI queries. So that's just a little bit, that I wanted to share on the lakehouse stackup. And in closing, I just wanted to say, our goal is ultimately to produce value from all of this data. And in order to do that, it's a combination of people and process and technology. But I think how you put those together into a pattern is super critical. And just was hoping to share this one pattern with you around the data refinery today. So thank you for attending that. And I guess we'll hand it off to you, John, to open it up for questions.
Yeah, great, Rupen. Thank you. Everybody down below, you'll see a Q&A, little Q&A link on Zoom. So feel free to type your questions in there. I do have a kind of a first question for you, Rupen, which is when you're thinking about just either a data lake or a data lakehouse model and the assumption of just, in essence, keeping all data in its raw form and holding it sort of in perpetuity so that you can do transformations on it later when you have, a better understanding of your needs. And so you can go back with a data science lab. Do you have any kind of perspectives on what the lifetime of that data needs to be? And do you also have any perspectives on whether or not you go back and process against that data with newer models to see if there are more learnings? As new models emerge, you go back and test using a bigger and bigger data set. And then third part of that question was, are there fundamental limitations to that, or do you think that the systems will continue to get cheaper and allow the volume of that storage and at least the data lake part of it to continue to grow?
Yeah, great question. So on the first one, I think ultimately you want to keep the data as long as you can. Certain times contracts with customers don't allow that, so you have to get rid of customer data when they tell you. But as a vendor, we like to keep the data forever if we can, and it's super cheap to keep it. S3 is not that expensive, and then there's different tiers of storage with things like Glacier, where you can put it on even cheaper storage if you don't use it that often. So there isn't a lot of cost with most of everything we've done in terms of just keeping everything, and it becomes useful to the second point, which is when you want to reprocess it for new algorithms, you have to have it available, otherwise you can't use it for new algorithms. We found that we were doing a lot of development on new machine learning models all the time because we were trying to compete in the market on that dimension. And so we needed to keep all the data so we could retrain those models, compare them to past models, and just give everybody a flavor for what our models did. They would try to predict the likelihood that an individual would need one of the different service lines in a hospital, whether it's ortho or cardio, et cetera. And so we would need to take these different encounter records, cleanse them, put them into these profiles of individuals, and then train them against what actually happened and see if we can actually do a good prediction. And so we tried a bunch of different models over a long period of time, and this was a super valuable tool for us there in terms of doing that. And as far as viability long term, cloud really enables you to keep all the data, and the cost of processing the data is a function of the processing engine you use. As I mentioned, we use Spark, which meant that we could process and reprocess sort of ad nauseum with a fixed amount of cost. So we would pick 24 Spark nodes and say, okay, that's about what we need. We know we're going to need that. And we could just keep calling, sending jobs to those nodes as often as we wanted. Had we gone to sort of a pay by the drink model, certainly it would have gotten prohibitive to do all that exploratory analysis and exploratory computing, because you don't know what you're looking for. So you're going to just send random jobs there, and you're going to rack up some pretty big bills, which is why I think, having the lake house kind of in the right kind of economic model for your enterprise is a key part of the design pattern.
Thanks, Rupen. Next question is, what sort of reasonable latency do you see commonly expected within the lakehouse type analytics solutions? For example, is it reasonable to continuously populate the data lake but expect the analytics scope to be at best a couple hours old? And also wondering about overhead between data sourced and data available for analytics.
Good question. So, I think it depends on which set of technologies you're using. So if you're using something like a SQL database with dbt and Snowflake, certainly your latency is going to be a little longer. And I think it's reasonable to expect it's going to relate to the size of the data and the computation, but you're not going to see sort of near real time. Usually you're talking 15 minutes at best type of latency. If you're using something like Spark, one of the advantages is Spark has, as part of Spark, micro batching. It's called Spark streaming. And so there's some optimizations in how that works for sort of continuous use applications. So you can get some pretty low latencies. You're not going to get millisecond latencies, but you can definitely get minute or less latencies for the computation. That's provided that the actual work you're doing in the computation is something you can limit. In the case of what we were doing, where we were essentially building a master data management solution for the individuals creating those profiles, we had to access a lot of data in order to check whether something already existed. And that's a fairly expensive operation to try to do in a streaming fashion. But most organizations don't have to do that. And so I think for the most part, Spark streaming will allow you to do that. And Spark now, or Databricks now, has something called Delta Lake, which sits under Spark and supports streaming in a little bit more seamless way than what we used to have to do, which is a lot of manual management of files and tables that we could pump into Spark. And then the last question was about overhead.
The overhead between the data sourced and the data available for analytics. So I think I'm interpreting this as the overhead in cleaning the data from its raw form into something that's accessible for doing analytics, if I'm not mistaken. But the way we manage it is we take the raw data in and we apply minimal transformation to it to get it into its cleansed state. And that minimal transformation is simply, is it adhering to the schema we expect? And are there garbage values in some of the fields or not? And that's about it. And it allows us to put records in error buckets that are errored and look at those. And then the ones that are not errored, we just kind of pass on. So there's not a lot of overhead in terms of getting it cleansed. For analytics purposes, if you're talking about ad hoc analytics, the only overhead is really the computation you have to do to take the schema that you got in, the raw events, and turn them into something that the data scientists can do something with. So that's not necessarily system level overhead. It's just more kind of the work that a data scientist normally has to do, or a data engineer supporting a data scientist has to do. If you have any more specifics on that question, I can go down there too. Okay, Rupen, thank you. Keep the questions coming, folks. We have not so much a question, but a marketing statement from Emma at Actian, who says anyone with cost containment issues with Snowflake should consider Actian Avalanche. We guarantee 50% off your Snowflake bill. Outstanding. We appreciate always any portfolio company aggressively marketing in any venue. So Emma, thanks for your contributions there. And I think it does point out the sort of the unknown risks of some of these platforms. And Rupen and I had a pretty long and detailed conversation about sort of the diabolical cleverness of the Snowflake model, where quite frankly they issue and use a credits-based model that fundamentally divorces you from really understanding what your dollar consumption is, and they're framing everything in terms of credits. So something for everyone to keep an eye on, and that's been one of the magic of Snowflake has been that it allows people to get engaged at credit card levels, a couple hundred or even $1,000 a month, and rapidly scale up to millions without people really having a handle on it. Okay. Rupen, do you want to make any comments about that particular thing? Because I know you've dealt with that specifically.
Yeah. Funny story there. So for a brief period of time, I sat on a purchase request for additional Snowflake credits because the bill was going to be about $1 million a year on a run rate basis. So I just sat on it. I was like, yeah, everybody will figure out how not to spend $1 million. And then ultimately the head of sales for Snowflake called me and asked me for lunch. And so we went out to lunch, and he's like, you guys don't have to spend $1 million. You can spend less. You just have to spend an extra $350,000 with us to show you how to spend less than $1 million a year. I thought that was the most clever sales conversation ever. But the point is that you can get those bills up pretty quickly if you're not careful.
Next question is, do you have Delta triggers that will notify data managers of anomalous change sets when something unexpected happens? If so, do you see opportunities to use ML to identify anomalies in these change sets?
The answer is kind of. So a lot of the processing that we did, at least at Influence Health, was like massive loads of files from EMRs. And so we kind of watch those things pretty closely. We have all kinds of monitoring and logging on those, so we know when things fail. We can go and look at those. And we have triggers on the error buckets, so we know when things end up in the error buckets. So that's the kind of level of anomalous triggering that we did, was really just kind of monitoring the error buckets and monitoring for issues or crashes in the pipelines, if you will. Definitely, I think there's an opportunity to use ML on the cleansing side of things. And if you start to look at some of these tools that are in the market, that's kind of what they're doing. They're saying, when we see this file coming in, we think that these fields are actually mapped to these other fields. So the first file you got in from, or first table you got in from a source had the fields in this particular order. And then that same source sent you another file and the fields were in a different order. Well, they actually meant the same thing. They were just changed in order. So ML algorithms are pretty good at figuring things like that out, and there's tools out there that do that pretty well. And there's also tools that we use from a security standpoint in order to make sure that there wasn't any weird access patterns to our data lake. And I forgot what it's called. There's a tool on Amazon. It's essentially an ML-based agent that'll watch for anomalous access to your buckets and everything else. So that's another area for ML, is kind of security of your data.
Great, thank you. A bit of a follow-up question here on the earlier questions. Any thoughts on low overhead tools or experiences to stream data out of, for example, MS SQL Server DBs, and into a data lake, for example, something like AWS AppSync, evaluating ways to pipe data out of existing applications running SQL Server on AWS and into data lakes with a lean, fast, low-cost tech stack? Any thoughts there?
Yeah, so that's a good question. So let's kind of break that into, I say, two parts, right? So the first part is that you want to use a tool to get the data out quickly. The second part is the encoding format of that data. So when you're trying to get data out of a database, there's certainly different ways to do it. One is you can query the database, assuming you have all the fields in the tables that tell you if something changed. The other that's kind of more popular these days is what's called change data capture, CDC. And so there's a set of tools out there. Debezium is a popular one that will pull basically the change data capture directly from the database and push it to wherever you want to push it. You can push it to a stream like Kafka, or you can just drop it as files onto the file system. The interesting part is once you've gotten those change data capture records out, and to be concrete, a change data capture record is going to look like, some row with, has it been updated, or has it been inserted, or has it been deleted? So you've got these records now sitting somewhere in a queue or on the file system. You've got to do something with them in order to get them into your data lake and then ultimately process them. And that do something part is where a lot of us have spent a lot of manual effort. But now that's being sort of packaged and made easier to use and easier to do something with. So both Delta Lake and Snowpipe with Snowflake make it a lot easier to deal with change data capture records and pump them into your tables. So I would say, you can look at commercial solutions out there to source the data from the database. And then you can look at sort of the solutions that are best aligned with whatever data lakehouse you're using to transform them into the lakehouse. So some combination of, say, Debezium plus Snowpipe for Snowflake, or Debezium plus Delta Lake and Spark, for Spark. And there's other solutions besides, Debezium, but I just gave that example because it's a popular one. Let's see.
Okay. Rupen, thanks for taking questions so far. To our participants, I know that we're 15 minutes from your next appointment, but are there any further questions that you'd like to ask? I feel like I'm some sort of talk show host here.
Yeah, I kind of went through some of this stuff pretty quickly. So if there's a particular area where folks that are on the presentation wanted me to dig deeper, I can certainly spend a little more time doing that.
Okay. One of the things that I wanted to ask you, and this is a bit more of a business question, is that the idea of being a data lake house, as it were, kind of combining the movement towards data lakes of a couple of years ago and warehouses that have been around for a while. Snowflake likes to claim that this is kind of the word they're using. Do you have a feeling more generally that the pattern of a large scale data reservoir that basically is comprehensive and holds everything, as you said, in a lightly cleansed format, but then uses multiple pipelines on an ELT basis going forward into materialized views and other types of analytics? Is this a pattern that you see kind of spreading across multiple vendors? You've talked about AWS's approach to the same, or is it somewhat unique to this small set, or do you simply think this is the way it's going to be generally going forward?
Well, yeah, I think it's growing in popularity in terms of the pattern of the lake house. And I think that the term, I think, was initially coined by Databricks to describe what they do with Spark. And then, of course, Snowflake's kind of competing there because the two are sort of colliding in the middle as they both try to solve for the same set of problems. And then, of course, Amazon's got their solution with Redshift and Spectrum. So I think there's three viable solutions for a lakehouse. They do have trade-offs if you try to use them in sort of the wrong way. From a pure transformation perspective, like doing more complicated transformations, I think Spark and Delta Lake have the edge. Then the reason being, A, it's not just SQL, and B, their economic model, the cost is actually reasonable when you try to do it at scale. Snowflake, of course, all the calculations, computations are going to be done using SQL. And then secondly, the cost is not exactly that cheap. What the vendors, I think, and Spectrum is similar. It's still probably somewhere in the middle in terms of cost, but similar capability to Snowflake. The way Spectrum works is it's got sort of an add-on to Redshift, which is an OLAP database, and it allows you to kind of work with files directly on S3 and query them and transform them and put them into views inside of Redshift. So all three of those, I think, are viable depending on the size of the organization and the complexity of what you're trying to do and how much ease of use you want. I do think Spark has the edge in terms of a pure, long-term, scalable data lakehouse at reasonable cost. And and if you just look at those dimensions, it's probably the best solution. From a perspective of OLAP and reporting capability, of course, that's not Spark's strong suit. So you still need a strong reporting engine, such as something like Snowflake.
Great, thanks. We got two more quick questions coming in, and then we'll wrap it up. What do you see as the best options on the data catalog side?
I haven't looked at a lot of the commercial solutions out there. We used Glue. Glue was perfectly fine for everything we needed, but there are some commercial solutions out there that are sort of better at sort of governance and schema evolution and AI algorithms that can make sense of the schemas automatically. Can't remember the name of the company I came across, but if you just Google some of those data catalog solutions, I'm sure you'll find a ranking somewhere. But I can tell you Glue is pretty good for most people.
And I assume cleansing and normalization will be client specific. How do you scale it as the number of clients grows?
Yes. So two parts to that. One is, I think, on your side as the platform operator, you have to have your own schema into which you're going to normalize. So the destination has to be something you define, and presumably for whatever domain you're in, you can create a single set of schemas. So everything will always go into those schemas because that's what your domain speaks. So that sort of limits one side of the equation, the target schema. The source schema, of course, is going to be different for different customers. And there's a couple different ways you can handle that. If each customer is going to send you a different kind of incoming file format, you're going to have a subsystem like this data sourcing system that can handle a mapping for each one of those clients. And so something that we did, because we actually had that problem, was to create a little mapping layer inside of that sourcing subsystem that could look at files and, depending on the customer, map certain fields into our own sort of internal representation that's normalized, so that we didn't have to deal with it anywhere downstream, kind of dealt with it up front. Sometimes there's sources that are coming from, say, your Facebooks and your Googles and all these different websites and sort of public utilities out there. Those you don't necessarily have to do transformation yourself. You can just use something that exists, whether it's your stitches or your Fivetrans or your segments that already speak those languages. And again, they'll normalize it into your schema so that on the target side, you're only dealing with one schema.
Okay. Similar question on the data ingestion as a service. This is best options on data ingestion. You may have just answered this. How important is the cleansing component? And is Spark the best answer for that? Or are there other tools you've considered? I think you may have just covered that. I'm not sure.
Yeah, I mean, I think it depends a little bit on your domain. I think for a lot of companies, using an out-of-the-box solution like a Stitch or Fivetran or one of those is probably a good option. The challenge is latency with those solutions, scalability, and of course cost, because you're handing that off to somebody else. So if you're not getting a lot of data in, but you're getting a lot of variety of data, I think those solutions are pretty good just to use as a service. If you're going to get a lot of data in, like what we did at Influence Health, I mean, that was kind of our business. Those solutions weren't very viable for us. The latency of it, the cost of it, and just the scale of it was a little bit bigger than what we could use or that we could put through it. So, so we use Spark. So I think you got to look at what your company is doing to kind of decide if you can just go ahead and use one of those off the shelf, or if you can, or if you're going to have to build your own subsystem for that.
Okay, Rupen, thank you so much for your time today. Deeply appreciated. We kept everybody, pretty much the entire group, the whole minute. So a lot of interest in what you're doing here. If everybody on the call, Rupen, are you okay sharing the presentation out with the group if they have questions?
Yeah, absolutely.
Okay. And if anybody wants to connect with Rupen directly, you can connect with me or with Christine or Su Yin, and we can give you Rupen's coordinates. and some of you already are connecting with him anyway. So anyway, on behalf of SEP and behalf of everybody here today, many thanks for your time this afternoon, and thanks everybody for joining. Hopefully this was a insightful session on a Friday going into a nice weekend. Talk to you soon.
Thank you, everyone.